There are some other types of, solution chemistry reactions that we should be aware of. There's also gas evolution reactions. Gas evolution reactions produce a gaseous product. So like with precipitation reactions, we observe a solid, falling out of solution. In this type of reaction, we observe gas being produced. Namely, we see bubbles. Right, so that's the idea. A lot of these gas evolution reactions are acid-base reactions. I'm not going to stress them too much, but we should be aware of them. So, for instance, as some examples, if we have hydrochloric acid, it can react with sodium bicarbonate. And what that produces, if we think about our ion swap, it's still that same type of chemistry, at least to begin. Right? Bicarbonate is HCO3 minus 1. We get carbonic acid. And sodium chloride. That's aqueous. So that's the first reaction, but then what happens is the carbonic acid goes on to produce CO2 gas and H2O liquid. So we would call this, really an intermediate product, right? It's not the final product, it's an intermediate product. And here is our gas evolution. So the carbonic acid just naturally degrades into CO2 and H2O. There's a couple of these that do the same, similar processes. We could take HCl and react it with sodium bisulfite. Bisulfite. And again, we're just doing a simple ion swap, swapping our pluses with our minuses, and we end up with H2SO3 plus sodium chloride. So again, we have this notion of the intermediary product. And that intermediate product actually goes forward to produce SO2, sulfur dioxide, and H2O. Right, so this is our gas evolution. And that would smell like rotten eggs. It's SO2 that you're smelling there. So there's a couple examples of these, different types of gas evolution reactions. The other reaction in this particular module that we need to discuss is then redox reactions. And redox reactions involve one starting material being reduced and one starting material being oxidized. And then that is really that's really our defining feature of redox, right? That we have a reduction and an oxidation. So our reduction is an element gaining electrons, and an oxidation is an element losing electrons. And you bring those two together, we have redox. I used to remember this from high school. Oil rig, in terms of a way to kind of remember that, where you have, oxidation involves loss, reduction involves gain. And in both cases, right, we're talking about loss and gain of electrons. And, that was an easy way for me to remember that in high school. And maybe that's an easy way for you to remember it here in terms of what's occurring. Oh, yeah, that's oxidation, that's loss of electrons, etc. So this is almost like acid-base chemistry, where you have opposites, right? We have acid, H+, reacting with base, OH-, and they make H2O. Well, here our partners are things that want to undergo a reduction or want to undergo an oxidation, that these elements want to lose electrons or gain electrons. And we've talked about that idea already to a good extent in terms of periodic trends, right? That, a lot of metals like to lose electrons, right? They have low ionization energies. A lot of the nonmetals don't like to lose electrons. They like to gain electrons, right? Because of electron affinity. So we have, that idea of certain elements in their chemistry as far as what they want to do in terms of losing electrons or gaining electrons. Now, in order to recognize a redox reaction, and it can be tough to recognize, basically we need to start to observe or see changes in oxidation numbers, right? And so we now have to kind of expand on this idea of oxidation numbers. So oxidation numbers basically relate to us an element's oxidation state, the actual oxidation state that it's in. These values, these oxidation numbers, can be either plus or minus, and they're integer values, so you're not going to see 1/2 or 1/3. You're going to see +1, +2, +3, or -1, -2, -3, etc. And it's changes in oxidation number in going from starting material to product that, basically allow us to know what is being reduced and, what is being oxidized. So we have to have some rules for putting these oxidation numbers together. So the first rule, elements in their natural state have 0 for their oxidation number. So like sodium solid or chlorine gas, or nitrogen gas, or iron as a solid, right? In terms of our oxidation numbers, these are all 0. For the chlorine, it's diatomic as well as the nitrogen, and it's 0 for both the elements within that. Both chlorines have a 0 oxidation state in Cl2. Both elements have, of the nitrogen, have a 0 oxidation number as well. Monoatomic elements with charge, their charge is equal to the oxidation number. So if I have, sodium +1, or if I have Cl -1, or iron +3, right, in terms of our oxidation numbers, we would have +1. I'm just going to put these in parentheses to help separate. -1 for the chloride and +3 for the iron, right, in that terms of oxidation number. In molecules, the most, or let's say it a little bit differently, the least electronegative groups, or rather electronegative elements, receive a positive oxidation number. These are basically, these are normally elements found in the beginning or in the beginning of a formula. There are some go-to elements, which have, you know, constant, positive oxidation numbers in molecules. And so I like to highlight, you know, those types of elements. And these are ones that we've talked about before, right, with group 1A, right? These oxidation number that they like is +1. Group 2A, right, our oxidation number they prefer is +2. And then group 3A, the oxidation number they like is +3. So those are just looking at those, you know, alkali earth metals, as well as then our group 3A elements as well. So if we're looking at, you know, periodic table, right, we're looking at, you know, with group 1, you know, you're looking at hydrogen, lithium, sodium, potassium, right, etc. With group 2, right, we're going from beryllium to magnesium to calcium, strontium, etc. And then with group 3, we're looking at, you know, boron, aluminum, gallium, indium, etc. So those are all really good go-to elements when we get to a molecule. So, you know, the least electronegative receives a positive oxidation number. In molecules, you know, the most electronegative elements receive a negative oxidation number. All right, these are normally, you know, at the end. And so we have not necessarily completely go to elements here, but we can kind of summarize. You know, group 7A, their oxidation number that they tend to prefer is -1. Group 6A, their oxidation number they prefer is -2. And then with group 5A, the oxidation number they prefer is -3. But remember, it has to be the most electronegative element, right? So as far as, you know, go to, you know, elements with, you know, defined negative oxidation numbers, there's really only two. There's fluorine, which has an oxidation number equal to -1. Fluorine is the most electronegative element. And oxygen, which is the next most electronegative element, it always has an oxidation number of -2, unless somehow it's paired with fluorine in a particular, you know, example. But those are the go-tos. We have to be careful because these are going to get the negative oxidation number. We have other elements within these groups above 7A, 6A, and 5A that are less electronegative than the fluorine or the oxygen. So remember, you know, it's the most electronegative element that gets the negative oxidation number, and then all the other elements must be more electropositive or less electronegative, and so they're getting the positive oxidation number. And then finally, the sum of all the oxidation numbers must equal the charge on the molecule. So let's do some examples of just assigning oxidation numbers. Let's look at CO2. So if we look at carbon dioxide, I'm going to be putting, oxidation numbers here in red, and in brackets, I'm going to have, sum of oxidation numbers. So if we look at our oxygen, oxygen is our go-to element. It's going to have a -2 oxidation number. But if we count how many there are, there's actually 2 of them. So I need to multiply by 2 because there are 2 of those oxygen elements in the molecule. That means that my carbon must be in this +4 oxidation state, or have this +4 oxidation number. Notice here that the sum of these is equal to 0, and our molecule is neutral. So that works out just fine. So that's how we have to be able to assign these different values for our oxidation numbers in molecules. Let's do a few more here. Let's look at sodium hypochlorite. We begin, our sodium, this has to be +1. There's our go-to metal. Here is our oxygen. It must be -2 because it's group 6A. It's also the most electronegative element. It's more electronegative than chlorine. So that means our chlorine must be in a +1 oxidation state. Again, notice that the sum is equal to 0 because we have a neutral molecule. Here we have sulfurous acid. Assigning its oxidation numbers, we would have +1 for our hydrogen. It's in group 1A. It's a go-to element, and there are 2 of them there, so I want to times that by 2. So there's 2 hydrogens. If I go to the far right, I have my other go-to element, which is my oxygen, which is -2. With that fact that there are 3 of those oxygens is why I need to multiply that oxidation number by 3 to get now a total of -6. And notice that this molecule is neutral, so that means the sulfur must be in the +4 state as far as its oxidation number. Again, this is a neutral molecule. It's no charge, so the sum is equal to 0. Do at least one more here. Here's manganate. If we look at this particular molecule, we now see that we actually do have a charge associated with it. And if we start with our oxygen, again, there's our go-to element. It has a -2 oxidation number. and there's 4 of them, so we would have a total of -8 for the sum of all of its oxidation numbers. That means that the manganese here must be in the +7 oxidation state. Right? Realize that the sum here is equal to -1 because molecule has a -1 charge. Do one last example here. Do ammonium. So ammonium has a +1 charge, and if we start with our hydrogens, we have that +1 oxidation state. There are 4 of them there, so we have a total of +4. And so that means the nitrogen is going to be what we would expect. It's the most electronegative, and it's in group 5A, and so it would have a -3 oxidation number. So there we see, the -3 and the +4. Our sum is equal to now +1, and again, because now the molecule has a +1 charge associated with it. So in order to recognize redox reactions, we have to have this ability to assign oxidation numbers. Now let's look at, redox reactions. And so we can just start with examples. So, you could ask yourself, is this a redox reaction? And what we want to do is assign oxidation numbers. Right? And then we want to look for a change in that idea of oxidation numbers. So if we assign, we would have +2 for the zinc, +2. Nickel's in its natural state, so it would be 0. Nickel then turns into +2, and the zinc now is back into its natural state, or 0. So if we break these two ideas down, we see the zinc +2 going to zinc 0. This is a gain of electrons. This is an example of a reduction. If we look at the other player here, which is the nickel, we would observe the opposite process in that change. Now we're going from 0 to +2. So that is a loss of electrons. And so that is our oxidation. So the zinc +2 is being reduced. and the nickel is being oxidized because of that change. There's some other terminology that we should understand. One is the oxidizing agent and reducing agent. The oxidizing agent is the element that is undergoing the reduction. It is pulling electrons from the other element causing that other element to be oxidized. So you can say it's the agent of oxidation or oxidizing agent. The reducing agent is just, the other side of the coin. So this is the element that is now undergoing the oxidation. Right, it is supplying electrons, right, to the other element, right, and that's causing the other element to be reduced. So you could say it's the agent of reduction. So there's some other terminology. Let's do one more example of a redox reaction. And look at, again, this identification process. So again, we could ask that kind of question, is this a redox, reaction? And so again, we need to, assign oxidation numbers and look for, a change. All right, and that tells us that, okay, we have redox. So going above to assign these oxidation numbers, we have the manganate. We actually already did an example of that above, right? Our oxygen is -2, but there would be a total of, -8, right? Since there are, 4 of them, that means our manganese is in that +7 oxidation state, or has that +7 oxidation number. Lead is in its natural state, so it has 0. If we go to the products, we have our lead oxide with our oxygens having a total of -4. So that means our lead must be in the +4 oxidation state. And if we look at the last one, manganese, it's monoatomic. It has a charge of +2. And so that's its oxidation state. And so now, it's that idea of recognize change. We see changes in manganese and lead oxidation numbers. So yes, right, this is redox, or this is a redox reaction. And we can recognize that by just pulling out the individual pieces, right, showing that the manganate is really turning into manganese plus 2. And we have that plus 7 on the manganese turning into plus 2 on the product side. So that is a gain of electrons. So that's our reduction. And then the other player, the lead, going to lead oxide, we're going from, this 0 state to a plus 4 state, and that is a loss of electrons, and that is our oxidation. So, not that you need to break it out this far, but what we do need to do is realize that there is a change in oxidation numbers, and that helps us to recognize that we have a reduction oxidation process occurring. So crucial to this in recognizing that you have a redox reaction is really the assignment of oxidation numbers. So that's it for this module on solution chemistry.